Thank you, Bill. Good afternoon. Okay, so I will apologize because my title looks different from the title on the list. And there's a reason behind that. Okay, so my name is John Wen, and I have a lab called the Laboratory for Emerging Energy Research. And I really look at the boundary between the recycle and the energy recovery. So therefore, there's a way to look at whether the municipal waste is a fuel feedstock or the raw material. And if you teach in the university, so you have to start with one equation. Here I selected this famous equation here, right? So we have this famous Einstein's equation, and it's natural to think about the link between material energy. So we want to get the energy out from any material, include solid waste, right? And before that, so give the carbon here, so that tell me, so I'm going to talk about the carbon only. So carbon chain and carbon-hydrogen chain and carbon-oxygen chain will be the source for the energy production from waste. And then I have one slide talks about my background. So basically, I'm a combustion guy, and I talked to a few colleagues here, and I'm new to this workshop, so it's the first time for me to attend this workshop, but I learned a lot. So I started from combustion research, then look at how to reduce the NOx or SOx and even particulate matters from the combustion process. That's kind of one side of energy research. On the other side, I use some fuels as the source of energy. Then we can make some nanotubes or nanoparticles from combustion. So that's kind of one research in the energy side, another research on the nanomaterial side. So hopefully my talk will cover some aspects from this picture. Yes, I talk about carbon in municipal solid waste and look at this famous diagram here. So we have the composition of the municipal waste from different countries, but basically if you look at types, they are very similar. So we have some paper, so we have organics, so we have plastics, glass, metals, and also textiles and others, right? So depends on our country, we produce different amount, but the types are quite similar. So then you look at the source of energy, so look at the carbon, so we are looking at organics and also recycled materials. For example, plastics. It's very careful we look at these energy sources because some of them are renewable, but some of them are not, right? Plastics, well, we have small amount of bioplastics, but normally they are from fossil fuel, so they are not renewable, right? So that's kind of the baseline we will do our analysis. And if you teach thermodynamics, you have to get familiar with this energy flow. So that's from the very new one. It's not 2015 US energy consumption. So I would draw your attention, you look at the left side. So that's all the major energy resources, primary energy resources. Right? So at the end of the table, so you look at the red kind of side, you can have the rejected energy. So the percentage of rejected energy is 59.1%, and energy service is already about 38%. So basically, for any energy resources, we can only use less than half of the energy and put it into the service. So here, do we have something related to solid waste? So I would draw your attention to look at the coal and the biomass. So those are two major solid energy source we use to provide as a service, right? So and then we also say the thermal efficiency is not very high, so it's still below like 40% from big picture. And you talk about the waste to energy, so I just put the coal and biomass over there. From that energy flow, clearly for the coal, 91% of coal is used for produce electricity. And for biomass, we have about 30%, and mainly for the transportation, and also some other part for the industry. So you are going to kind of compete your solid with the coal and the biomass, and you have some guidance where I can use energy produced by the solid waste. And here shows the 3R, very familiar, and the interesting. So we place the recovery of energy after the 3R. We call it beyond the 3R. And there are generally those technologies, thermal treatment, gasification, pyrolysis, and digestion. So, and then you look at the energy forms produced from different technologies. Mainly, we have electricity, natural gas, and ethanol. So ethanol comes from bio part of the waste. So then you compare the use of coal and biomass. So if we use, for example, solid to produce electricity, how can I compare to the energy efficiency and also emission from coal combustion, right? So that's something we have to look at. And at least in Ontario, we don't have coal-fired power plants. So then do we need to have the solid waste powered plant, right? So challenges are obvious. So I don't expect you to read this table, but this is from a report. And here shows all the challenges from the thermal treatment of waste in order to produce energy. So mainly, you look at this, it's an air pollution problem, and also you have to look at the carbon sequestration. So only carbon sequestration, carbon footprint is neutral if you have renewables, right? So otherwise, you have to release CO2. And for example, you look at the plastics. So plastic contains some fixed carbon already. Then you pour plastics in order to reduce some energy, so release the carbon CO2. Carbon dioxide CO2 from the plastics, right? So those are real challenges. So we have to make some wise selection how to go with waste to energy. And mainly, so for organic solid waste, so if you want to use as a fuel feedstock, so personally, I think there are basically two choices you can make in between. So first one is cost effective. So you can just have a dejection, then produce the biogas naturally, or you have engineering devices, so you can produce it. You can use a biogas, okay, so as the secondary energy carrier. Or you have to produce liquid biofuels. Liquid biofuels can be used for transportation, and currently, so for example, even we have electric car, we don't have electrical airplanes. So airplanes definitely need some liquid biofuels, right? So there's famous technology, Anakin, I think maybe some colleague will talk about that. So there's developed technology so we can make the biogas and the biofuels. But here I only talk about organics. Then today I'm going to introduce 3 sample projects in my lab and maybe give you some ideas of what we are doing now. And again, so I'm new to the field, so maybe the projects are a little bit far from the direct waste to energy. So first one is the gasification technology. Secondly, so organics to biofuels. So we look at how to reduce the emissions further from the bioethanol combustion. Bioethanol you can treat it as biofuels, but still have emissions. The combustion still produce greenhouse gases and also particulates. We have to get rid of them. Thirdly, so that's something very new, and I'm going to talk about later. So how to use waste plastics to make the high-value products, such as carbon nanotubes. The first project is about the gasification. So we look at the conventional gasification and also plasma-assisted gasification. So here I just look at some lab-scale small gasifiers. And Jatin is one of the co-authors of this work. And I work with Professor Javad Maskimi at the University of Toronto. So we want to develop some understandable standard procedure in order to evaluate the energy and also the emissions. So also we want to develop some model in order to predict the emissions and energy conversion. So here we just look at the lab scale downdraft gasifier. So we have well-defined zones within the gasifier, so we can look at each step. So here shows that's the gasifier we bought from market, and mainly it has a gasifier itself, and we have a filtration that's on top of that wood box, and we need an air compressor in order to increase pressure within the gasifier because it's downdraft. So here I want to say, so we definitely need some electricity as input in order to gasify this biomass. So I haven't tried the solid waste, but we tried lots of different woods. Okay, so different biomass particles. Then we use a GC and a gas analyzer in order to measure the emissions from the gasification. So I don't want to go deep to this project. And here shows the Aspen Plus model. So we use to describe the energy balance, the material balance, material flow during the gasification, and with the 4 separated process, right? Then we can have some very detailed CFD modeling. CFD is computational fluid dynamics modeling. So you can model the flow within the reactor. So here we can predict the mole fraction of hydrogen and carbon monoxide. So that's basically, thank you. So that's the concentration of syngas. So that's the major product of the gasification. Yeah, so we have this facility and modern tools are available. So if there is a need, so we can help to look at the material and energy balance from the solid waste gasification. Then finally, so we have this single slide. So we work with Professor Javad, Maskimi from the Toronto. So we look at how to use a very powerful plasma torch in order to process e-waste. Here shows the bottom 3 figures tells us, so if you use a plasma to treat the copper on some plastic or polymer, then you can fully recover the copper from that material. And we recently submitted an ORF proposal based on this. So basically, you have to optimize the geometry and the parameters of the plasma torch. So that's all for the gasification. The second project is about the combustion and emission controls of bioethanol, as I mentioned earlier. So we still need to develop some emission control technology for the biofuels. And this project has been supported by the Biofuel Net, and Biofuel Net just submitted the renewable application to NSERC, so the NCE actually. So, and I work with a company called WastetoEnergy. So basically, so we want to add some nano catalysts in order to reduce the emission from a bioethanol. So first of all, you have to characterize the combustion properties and also emissions from bioethanol. Then, so we can look at, do we have some new technology developed in order to reduce the emission? So here is my facility. So I have a counter-flow flame burner. So you can see that very beautiful single sheet of flame. So there you have freedom to measure the emissions at each location. So we use some gas GC and FTR in order to identify the species and greenhouse gases. And also we use some material analytic chemistry method in order to look at the nanoparticles, particulate matters produced from the combustion. And here just shows one example. So we put in that precursor, and precursor is going to produce some nanoparticles. These nanoparticles you're going to use to calculate, so to produce the less NOx from the combustion. Here shows if you use this kind of catalyst, so basically you can reduce 25% of NOx from that flame, same flame. Then quickly I go to the third project. So plastics for single-wall carbon nanotubes. And I work with this nano-C starting from my postdoc at MIT. So they kind of produce lots of high quality but low cost single-wall carbon nanotubes from combustion process. And you look at the web page. So there's lots of news about use waste plastics in order to produce carbon nanotubes. So you can use waste plastic bags directly. Lots of bags. Even the ABC, they have some video about how to turn the waste plastics to carbon nanotubes. And that's the latest article published by NanoC, my partner, about this project. So just very simple to explain the principle of how to use the combustion to make carbon nanotubes. So basically, carbon nanotube consists of carbon. But you have a very organized carbon structure. Therefore, in order to produce that structure, you need energy, you need carbon, and you need catalyst. here shows if you have combustion flame, so you put in some catalyst, then the carbon source in the flame, for example, CO or like a methane, C2H2, they are going to react with the catalyst. Just accumulate on the surface catalyst, they are going to find the good location, then they are going to grow into the carbon nanotube. So the principle is very straightforward, but the key is you have to control the formation of a catalyst and the formation of a carbon nanotube simultaneously and very accurately. So here just shows the tubes you produced from combustion process. The SEM, the bottom SEM image clearly shows the nanotubes network produced by the combustion process, and TM shows the diameter and the length of the carbon nanotubes. And AFM gives us the morphology of each tubes. And also there's some catalyst attached to the tubes. So then come back to my topic. So municipal solid waste. So again, so we have to make a wise choice whether use it to produce energy or you should spend more time in order to sort it out and use it for recycle. So I guess my personal, at this moment, very preliminary conclusion is that for the organics renewables, definitely we should look at what, in addition to other options, we should look at how to make biofuels. And for the plastics, other non-renewables, maybe we should look at how to use as the recycle or feedstock for the material. Thank you so much for your attention.